Okay, welcome to the next lecture, lecture 12 of numerical analysis of ODEs. Just to remind you from the last video, we were finishing our discussion of the three different stability properties I discussed. So we had started with A stability, which is something defined for linear ODEs, and then looked at the very intuitive B stability, and showed the relationship between A stability and B stability, in particular that B stability always implies A stability, and then finished the section with also introducing L stability, which also is sometimes called asymptotic A stability. And then we started looking at methods that are stable. In particular, we extended our definition of explicit Runge-Kutta methods to the full set of general Runge-Kutta methods in the most general sense, the IR case, the implicit Runge-Kutta methods with full stage matrix A, and then the simplifications, the Dirks, which are those where the upper right triangle of the stage matrix is 0. So we basically only ever depend on the current stage value and not on future stage values, which makes it a little bit easier to solve. And then S-Dirks, or symmetrically diagonal, or sorry, oh, forgot the word. Singly diagonal Runge-Kutta methods, which have the same diagonal on all stages. And the first thing we saw when I wrote down the first general implicit Runge-Kutta method is that implicit Runge-Kutta methods are able to achieve higher order consistency order than the number of stages. So with explicit Runge-Kutta methods, remember the Butcher barriers, which said that we basically have P no bigger than S, in fact sometimes even smaller than S for higher order. This is not true for implicit Runge-Kutta methods, and we will get to significantly larger orders later. Then I showed what the general stability function looks like for general Runge-Kutta methods and gave some examples. First of all, just looking at ERCs again, and in the case of ERCs, the stability regions are always polynomials, which is also how we proved that they cannot be astable, because polynomials will never have, cannot be bounded on the whole left complex plane. And then finally, so we had already seen the implicit Euler method before that, but then we looked at the extension of the implicit Euler method to the so-called theta scheme, which is a parametrized family of Runge-Kutta methods that interpolates in some sense between explicit and implicit Euler. And for a half, theta a half is called the Crank-Nicholson method. And we showed that all the theta schemes for theta bigger than or equal to a half are astable. Okay, so now we're in the section of section 3.3.1 on the existence and uniqueness of discrete solutions. So it's all fine well that we now have more stability, but as I said, we've bought it by solving nonlinear systems, having to solve nonlinear systems to get the stage values. And in fact, what we will see now is that that imposes again conditions on the step size. So we've tried to get away from conditions on the step size by moving from explicit to implicit methods, but we're buying it with solvability conditions again on H. So here again, H cannot be arbitrarily large. Okay, so this is the first of three results I'm gonna prove, and one of them I'm just gonna quote. As I said, this is the first one here, lemma 3.39, is the most simple and the most general, but it is also the most restrictive. So let's assume that f is Lipschitz continuous in its second argument on the whole of our R cross Rd with Lipschitz constant L. Then if the step size is less than 1 over this Lipschitz constant and times the norm of the matrix, for any initial condition, why not? The Runge-Kutta method, the general Runge-Kutta method, has a unique solution, y1. Okay, let's prove this. So as typical with these sort of solution of nonlinear systems arguments, we prove it via a fixed point argument. So let y naught be given in Rd and define the matrix of stage values k to be k1 up to ks in R d cross s. So each of them is an Rd vector. If I concatenate them or put them together in the matrix, it's an Rd cross s matrix. So if you don't remember the formula for the general Runge-Kutta method, please pause and have a look back at 322. So given some initial matrix K naught, so that's our fixed point argument now. So we start iteratively with a starting guess K naught, and then consider the fixed point iteration Km is some function or some operator psi of Km minus 1 for m equals 1, 2, etc., which is defined column-wise by Kim is psi I, the ith column of the operator psi, being given by its formula, but evaluating the right hand side. So remember, it's implicit, so it depends on the value of k. So we plug in the previous iterate here. So we simply iterate the formula. Okay, so highlight this. So here we stick in the m minus first argument. So here we have got the mth argument. Okay, and this would be obviously for every stage. Which obviously clearly has the matrix of stage values k as a fixed point. That's how the matrix K is defined in 322. So now we need to check the usual conditions for fixed point argument, namely whether we have a contraction, whether psi is a contraction, because then we can argue that there is a unique fixed point in a certain ball. Okay, so using a certain norm in order to define the ball and distances, using on RD cross S the norm defined by maximum I equals 1 to S Ki. Ki is a vector norm, namely the Euclidean vector norm is the regular Euclidean norm on RD. Remember, we can make these fixed point arguments always for any norm on a normed space. From the Lipschitz, well, on any Banach space we need to have a complete space. It follows from the Lipschitz continuity of f that we've assumed in its second argument that psi of k minus psi of k primed is less than or equal to, so we can now use here the Lipschitz argument column-wise, because we're looking here at the maximum over all the column norms, so we can just look at the individual norms. This is less than or equal to, let's just write it out, then it's easier. Max I equals 1 to S psi I, which is f of, I'm not going to write it out, otherwise it's going to get too confusing. Ki Euclidean norm minus Ki prime, sorry, is less than or equal to so we pull out the h here from this guy, we take the Lipschitz constant, so first of all we take the Lipschitz constant, then we pull out the h from this argument here, and we end up with the maximum over these sums here. So the maximum j equals of I equals 1 to S, sorry, that's the maximum that comes from this maximum here, and then the sum j equals 1 to S modulus Aij, and then I'm only left with the kj's, so I'm left with kj minus kj primed, and I can obviously take the max of that again, and so that's less than or equal to L times H times sum j equals 1 to S Aij k minus k primed. Okay, just pulled out the max of the kj primes. the right. So under assumption 327, which I didn't give a number. So this is assumption 327. Under this assumption, namely that HL times the A norm, the infinity norm of A of the stage values less than 1. So this thing here is, or the max of this, I forgot the max, I left the max away. Oops. So here the max, I forgot. So max I equals 1 to S. Well, let's put it straight away in here, in fact. So this thing here is nothing else than the infinity norm of A. So this is L times H times A infinity norm times K minus K primed in that other matrix norm we defined. So under assumption 327, the Lipschitz constant, or let's put it in parentheses like I did in the notes. The term in the parentheses is strictly less than 1. And thus psi is a contraction and then we can just apply then the fixed point argument. So that would be theorem A.3.1 then yields the unique solution. Okay, and thus the unique y1. Remember, the y1 in 322 was simply a linear operation. So after we've computed the stage values ki, then y1 is just y0 plus h times sum over the bi's, ki's. So we have proved that under this condition of Lipschitz continuity and condition 327, the Runge-Kutta method has a unique solution. But as I said already in the discussion at the start of this subsection, this is very restrictive because remember, for stiff ODEs, L can be very, very large, and therefore we want to have and also the Lipschitz continuity condition is obviously restrictive, but that one is less so the problem, but we don't want to have such small time steps. So we want to work again with the one-sided Lipschitz condition 3.3. So let's now consider f again to be continuous differentiable and as a function of r cross cd to satisfy a one-sided Lipschitz condition on the second argument with constant nu. And remember, for stiff ODEs, we have that nu is much, much less than L modulus. In fact, nu for stiff ODEs is always negative or 0, and therefore we're talking about very small. Nu is sort of the eigenvalue that's closest to 0, the largest eigenvalue, the smallest negative eigenvalue, and L typically represents the largest negative eigenvalue. Then consider an arbitrary Dirk. So we're only going to look at methods that are diagonal implicit Runge-Kutta methods with positive diagonal entries AII. Then we have the much less restrictive condition that H nu times AII should be less than 1. So for a start, we have obviously that modulus of nu is much smaller than L. Secondly, if nu is negative, then there is no constraint at all. And thirdly, the AIIs we have are basically only the diagonal entries and can also be much smaller than the full matrix, full norm of matrix A of the stage values. Then for any y0 in CD, each of the decoupled nonlinear equations in 322A has a solution GI. So we see that for stiff ODEs, in essence, we have no constraints here. Okay, let's prove this. So the proof simplifies compared to the proof for general implicit Runge-Kutta methods, since each stage. So before we had to put everything together into a matrix of stage values, but here each stage depends explicitly on the previous stages and only implicitly previous stages and implicitly only on itself and not on future values. So that's the big difference. And thus, for this case, we can write a bit simpler. So we simplify the notation by writing GI is y0 plus VI plus the final value, namely HII f of GI. I should really write, don't know why this is not done here, f of T0 plus CIH GI. Let me just double check. Yeah. Where the important bit being that we set VI, we substitute the previous stage values here. So j equals 1 to I minus 1, a I j f of t naught plus c I c j h g j. That's 329, that's 328. So this is 329. So let's start with linear initial value problems. For linear initial value problems with the right hand side being given by, let's say, for linear autonomous, I should say. But remember, we can always autonomize for Runge-Kutta methods. So for linear autonomous initial value problems with f of ty being m matrix m times y with diagonalizable system matrix M. I show this just so that you see the simple linear case first, and then I'll do the proof for the full general case. So identity minus, if we look at this formula here, identity minus HII M GI is equal to Y naught plus VI. And now, since we know that for linear initial value problems, the nu in the one-sided Lipschitz condition is just the maximum overall real parts of the eigenvalues of the system matrix M. You can find that proof in lemma 3.1.8. So since we know this, it follows from assumption 328 that all eigenvalues of the system matrix here of I minus HII M have positive real part. If I look again, so the condition is that H nu AII is less than 1. We know that the nu is the maximum of the real parts of the eigenvalues of M, and so the matrix multiplying by H AII and then subtracting from the identity has to have can only have positive eigenvalues with positive real part. And then that gives us the result, because thus the inverse exists, because it's positive definite, and we obtain a unique solution. Okay, now this was only in the case of linear autonomous initial value problems with diagonalizable system matrix M. So it's a very particular case. In the nonlinear, or in a general case, in the general nonlinear case, we use a homotopy argument. So first of all, I should say we autonomize the ODE, the initial value problem. I didn't write that explicitly. We autonomize the initial value problem and use a homotopy argument. Oh no, I don't need to autonomize. It's just another set of typos, sorry. So introduce the parameter tau. That's going to be our homotopy parameter. So for those who have never seen a homotopy argument shows you that if you have a homotopy parameter tau that goes from 0 to 1, and you know a solution exists at one end of this spectrum, so if for tau equals 0, typically you start with a problem that you know has a unique solution, and then you move the parameter tau smoothly to the new problem, and if you can show that this function that moves, the homotopy function that moves it, is smooth or has bounded derivative, then you can show that the other endpoint also has a unique solution. So we introduce the parameter tau in 0, 1 and set up the family of problems, of equations. So this is now our homotopy function g tau, and g tau is essentially y naught. In fact, we could have used the step size h as a homotopy parameter as well, but I'm just going to introduce it as tau vi plus h I f of tau and g of tau plus tau minus 1 times h. In fact, I'm not going to do this as tau here, otherwise we're going to get into trouble. I'm going to use f of t plus cih g of tau plus tau minus 1 hii f of it is autonomized. I knew it. Okay, so without loss of some, let me just put that in here. You know already anyway. We assume without loss of generality that the initial value problem is autonomous. Otherwise, we need to autonomize, and we need the conditions to hold such that the Rogue-Kutta method is invariant and an autonomization that we proved before. Okay, so let's forget about having the time dependence here. That makes it a lot easier. The argument obviously goes through if I do it directly as well, because all I'm doing is a homotopy argument in the parameter, in the time parameter, which I could have also done directly in the first argument rather than autonomizing before. Okay, so we basically take, so the important bits are that here we only take tau times vi, and we only take this f at g tau, but we correct it for by having this tau minus 1 times the value at the previous time step, namely y naught. So we always do homotopy away from y naught for every stage. So for tau equals 0, this equation clearly has the solution g of naught is simply y naught. And for tau equals 1, the solution g1 is equal to y1, gi, sorry. Now, provided g prime, as I said, is bounded, on 0, 1, we can conclude that the solution gi exists, since we can use simply fundamental theorem of calculus to say that g1 is g of naught plus integral from naught to 1 g primed of s ds. That's 330. Now, to show that g primed is bounded, we note first that f was assumed to be differentiable. So that implies that we can simply take derivative of f and make it explicit with respect to y times h we're autonomous, so I'm just going to do this cleanly. So f primed t y autonomous f prime y h plus little o of modulus of h. So we have to do, this is all vector valued, remember, inner product, Euclidean inner product with h is equal to f of y plus h minus f of y inner product with h, and now this is exactly what we have in our left-sided Lipschitz condition. So this is less than or equal to nu times modulus or Euclidean norm of h squared. Now dividing by So here's a few typos we need to correct. Dividing by h squared, norm h squared, and taking the limit as norm h goes to 0, we can obtain with unit vector h hat being defined as h divided by modulus h that the Jacobian matrix, so the derivative of the vector valued function f with respect to y times unit vector h against unit vector h is less than equal to nu, or equivalently, not working in unit vectors, we can also multiply again by h squared once we've taken the limit and say that for arbitrary. So in order to take the limit, you need to go to these unit vectors, but then you can actually multiply by h again, and you can find that this is less than or equal to nu times h squared for all h in CD. So we can now plug it into G primed. Where's G here? So we want to take the derivative of this function with respect to tau. So we get vi from here, we get hai f of y naught from here, and we need to take the chain rule here. So hence, with G primed of tau being vi plus chain rule here hii f primed of g of tau g primed of tau plus hai f y naught. So that's the second term, or last term in the homotopy function. We obtain norm g prime of tau squared can be written as inner product, Euclidean inner product of vi plus h ai f primed g of tau g primed of tau plus hai f y naught with g primed of tau. I pull out the terms that do not depend on g primed on the left, so I get vi plus hai f of y naught inner product with g primed of tau plus, and then I'm left with h ai, and then we've just shown that this thing here is less than or equal to, well, let's write it out first, hai, I can pull that out immediately, hai inner product f primed of g of tau g primed of tau with g primed of tau. Now I can use this result we've just shown up here, or rather here, and take an upper bound. So this is less than or equal to norm vi plus h ai f x naught Cauchy-Schwarz times norm g prime tau squared. No squared, sorry. Cauchy-Schwarz plus h ai nu g prime tau, and this one is squared. Okay, so now we can subtract the second term on the right and dividing by 1 minus HAII nu. Let's write that on the next line. Dividing by 1 minus HII nu, which by assumption is positive. So remember, our assumption was that h nu I is less than 1. So either nu is negative or we have a constraint on the mesh size h. So since this is positive, so we've subtracted this term here on the left, and then we get 1 minus HAII nu. So divide through by 1 minus HAII nu. Then it follows that g primed of tau squared is less than or equal to the norm here vi plus HAII f of y naught divided by 1 minus HAII nu times g primed of tau. Hence, g primed of tau is either 0, which is fine, or bounded for all tau in 0, 1, and we are finished. Remember, we only wanted to prove that this g function, this homotopy function that we have here, has a bounded derivative, because then we can find g1, which is our stage value, from g0, which is our initial guess, by this simple fundamental of theorem of calculus rule. And we've just shown that g primed is in fact bounded, either 0 or bounded. So then this implies, okay, I don't really have space here now, but I'm just gonna fit it in here. If the Dirk method we just used in lemma 3310 is B stable or A stable, then that implies that GI is in fact unique. Okay, so we have a at least for Dirk methods, for the diagonally implicit Runge-Kutta methods, for stiff ODEs, we have solvability of the stage equations for arbitrary mesh size h, as long as nu is negative, and if nu is positive, remember stiff ODEs, we wanted very small positive nus, then we get not a very strict not a very strict condition on the stability here. But I'm gonna quote without proof a more general result, namely theorem 3.3.11 here. Let f be continuously differentiable again, and in the second argument, and let it satisfy the one-sided Lipschitz condition 3.3 with constant nu again. So the same we said before. Then we now look at arbitrary Runge-Kutta methods, not just diagonal implicit ones. If the Runge-Kutta method, if the Runge-Kutta matrix A is invertible, so that's a new condition we haven't looked at before, and if there exists a diagonal matrix D with positive entries, such that this condition holds, which clearly is a generalization of what we had before, because just look at it. So before we had h times nu times aii less than 1 for diagonal implicit methods. This thing here is, if you reformulate it, looks, or this could be seen as h nu less than 1 on aii, and this one reformulated just states h nu x d is less than x a inverse x d. So it's just in a particular inner product, in the product defined by D, we get a similar condition as the one above, but now we don't need to assume that we have a Dirk. We can have an arbitrary implicit Runge-Kutta method with invertible A. Then the nonlinear system 322A has a unique solution. Where this is just the inner product defined here, just to be precise. And as I said, I'm not gonna prove this. 51. So for the proof, you can look in higher end Wanna. We omit the proof and refer to. It is a very similar proof to what we just saw for Dirk's. It just is a little bit more involved, and I don't want to add this technicality here. Okay, good. So that was it with the solvability. So for stiff ODEs, we don't have any problems. We don't have any constraints on little h, and you see already certain new conditions popping up. So in particular, a good Runge-Kutta method should really have an invertible A, and then we have all ingredients that we need for running our for having a stable integration over long term periods. But before I go to constructing good implicit Runge-Kutta methods, let me just do some considerations on the implementation of Runge-Kutta methods, because we will come across immediately across a problem with Dirks. So we've seen in lemma 339 that implicit Runge-Kutta methods require the solution of a nonlinear system of size S times D. So basically, if we have S stages, then and D ODEs, we immediately get an S times D dimensional nonlinear system where we're computing all the stage values together. So where S is the number of stages and D is the number of ODEs, or the system size. Dirac methods, as we saw in the lemma 3310, are simpler and only require, well, it's slightly simpler, but it definitely makes a difference when you're solving nonlinear problems if you only require the solution of systems of dimension D S times. So you're solving S independent systems of dimension, nonlinear systems of dimension D. Thus, we should really prefer this class of methods, were it not for the following result. Namely, we have another barrier, and the barrier is called that B-stable Dirac methods can have order no higher than 4. So we're stuck with order 4 if we're restricting ourselves to Diracs. And so if we want really high order implicit Runge-Kutta methods, we do need to fill up also the upper triangular part of the Runge-Kutta method of the Butcher tableau. So this is theorem 413.13. I'm not going to prove it again. Okay. So we do actually, if we want higher order, we do want to look at full matrices and not just diagonal implicit Runge-Kutta methods. One more thing to add is the following remark before we get to this construction of general Runge-Kutta methods, and that's in is a stability consideration. So we're solving in each step of an implicit Runge-Kutta method. We have to solve a linear or nonlinear, even in the linear case this is a problem, nonlinear system for the stage values, for the quantities gi. So remember, the gi's are values of intermediate values of y. So if I'm going from y0 to y1 and I do a very small time step, I'm not expecting the solution to move much. So the gi's will differ very little. And so whenever we are subtracting a gi from another gi, or from a y0 or y1, we're gonna get round-off problems. So in order to reduce round off errors, it is advantageous to actually write the whole system in terms of the updates to solve for Zi, which is Gi minus Y naught. So we never actually compute Gi, we always directly work with the Zi's, with the differences. So then we always work with smaller numbers and we don't subtract two large numbers to get round off. So especially for small time steps, as I said already, especially for small time steps, Zi is expected to be much smaller than Gi. Thus we have to solve the following system written in terms of Z's rather than in terms of G's. So we need Zi is equal to H times, so the Y naught has been put to the other side, H times J1 to S Aij F of T naught plus Cjh, and then we immediately write this as Y naught plus Zj here. I equals 1 to S, and that's 332. Somehow I have the impression that I didn't write all the numbers down again. Yes, I think I didn't. Okay, let me just, I'm really sorry. I again dropped a few numbers. So here we had 330 still, but it was this condition here that I missed out. So this is 331. The most general condition on solvability is 331. Okay, so 332 is the system that we should really solve in order to avoid round off, and using the Runge-Kutta matrix of stage values A, we can rewrite this as Z1 to Zs is equal to A times HF of T naught Z1H Y naught plus Z1 all the way down to HF T naught plus CSH Y naught plus CS. This is 333. And then we can avoid further function evaluations by then computing the final solution y1 as y naught plus b transposed a inverse z. Or rather, actually, I think you don't want to do this. You want to write, you want to solve Okay, no, this is exactly what you want to do. y1 plus is equal to y0 plus b transposed a inverse z. So you first calculate the update, and then only do you add it to the final solution approximation at time step t1, which again is numerically more stable. Then evaluating f with a possibly large Lipschitz constant. Okay, so you evaluate the f, or you use the f only in the solution of this this system here. If it's linear, then this just becomes one big linear system here, and if f is nonlinear, then you have to solve a nonlinear system here in Z. Okay, so, and obviously, as you can see here, this, as in the last assumption, assumes again an invertible stage matrix of the Runge-Kutta method. Okay, so now we have all ingredients ready. We have discussed stability conditions. We have discussed the general form of a implicit Runge-Kutta method. We have discussed what certain barriers we have, and we found that we can get better consistency orders than with explicit Runge-Kutta methods by designing implicit Runge-Kutta methods. Now, in the final, or in the next chapter, sorry, not the final, in the next chapter of this chapter 3, next section of chapter 3, we now want to construct high-order Runge-Kutta methods, high-order stable Runge-Kutta methods, again using the relationship to quadrature that we've already highlighted at the beginning of the Runge-Kutta chapter. So we finish our discussion of Runge-Kutta methods by describing a systematic way. So far I've always just dropped some quadrature, some Runge-Kutta methods on you without really telling you how anybody came about finding them. Now we want to have a systematic way to construct stable, high-order Runge-Kutta methods. And the order conditions were quite involved, and we saw that they increased and increased over the levels. And so one way of making progress was by people defining so-called simplifying order conditions. These are order conditions that are sufficient but not necessary. But they are actually much easier to work with, and we're gonna use those conditions, or rather prove first of all that under these conditions certain order conditions are satisfied, or the other more complex order conditions are satisfied, and then use them to design methods on the basis of these simplified conditions. So these simplified conditions are equations 335. I'm going to subdivide them into 335a, 335b, and 335c. So the first condition is pretty straightforward. This is simply a condition on the if you think back at quadrature, if you do quadrature of a function on the interval 0, 1, then the monomials up to order q integrate to the value of 1 over q. And so this simply says that the bi's and the ci's should be chosen so that the order of precision of the quadrature rules is the Genauigkeitsgrad of the quadrature rule is p, sorry. So if you can satisfy this for q equals 1 to p, so for all monomials from 0 up to p minus 1, then that's the first order condition. So that means that essentially your final y1 formula has the right order. But we also need to get the right order on the stage values, and so the next one you see immediately is quite easy as well. The next one is nothing else but saying that the for all stages I equals 1 to s, where we're integrating from not to ci, so these are integrals on the interval. This is an integral on the interval 0, 1. These are integrals on the intervals 0 ci, and so this condition says nothing else than that the quadrature rule with coefficients aij for the ith point, for the ith stage value, has the right quadrature consistency. So it's exact for polynomials up to, again, order p minus 1 here. And then the final one is the one that combines the two, because we also extrapolating and then substituting back in. We had this discussion before, and this dp is essentially a condition that gives you some combination of the bi's and aij's here. Okay, but it's also again quadrature related. Okay, so we define these conditions bp, cp, and dp, and then the theorem. Why did I not leave myself any space here? I forgot. I need to add a slide somehow. Let's add a slide after. Okay, so then the following theorem holds under these simplified conditions. So consider a general Runge-Kutta method, and now we're not going to satisfy all those conditions with the same coefficient. So we need to satisfy 335a with parameter p. We need to satisfy 335b with parameter xi, and we need to satisfy 335c with parameter eta. And the p, xi, and eta need to satisfy these conditions. If that's the case, then the method has consistency order p. And as you can imagine, the proof is not trivial. And so we refer to the second book by Hira and Vanna, Hira, Norset and Vanna, 09, chapter 1. Sorry, not chapter 1. Chapter Roman 2, theorem 7.4. Okay, and as I said, we only observe what I observed already before, that integral 0 to the 1 t q minus 1 dt is 1 over q, and integral 0 to c I t q minus 1 dt is equal to ci q over q. So this is basically what I said earlier. So this condition simply states order of accuracy for the quadrature rule with the BIs, and this condition here simply states consistency order of the quadrature rule for the stage equations. Thus, if we insert the function x yx, okay, I need to reformulate this. This is not very clearly written here. I'll reformulate it in the way I've just explained it before. Yeah. Okay. So I've said in words already how to understand these order conditions, namely that this order condition here simply means that all monomials up to order p minus 1 are integrated exactly by the quadrature rule with quadrature weights bi and position ci, and this formula simply means that the quadrature rule with quadrature weights aij and quadrature points cj to integrate on the intervals 0 to ci all polynomials up to degree p minus 1 exactly is exactly this condition here. So that's what I wanted to say here. It's really badly written in here in the script. I'll rewrite this. Okay. So now we have these simplified order conditions, and now we can basically use our knowledge from quadrature in order to build good implicit Runge-Kutta methods. And so in order to do that, let us recall some of the things we know from numeric 0 or from your first numeric course on quadrature. So remember, for quadrature, maybe I'll write this here quickly. Have a look back at numeric 0. We started defining quadrature by looking at Newton-Cotes rules. For Newton-Cotes, we had equidistant quadrature points, which here would be the values ci being equidistant. And we also found for quadrature rules, or for Newton-Cotes quadrature rules, that Newton-Cotes had basically the order of accuracy, der Genauigkeitsgrad, the order of accuracy was essentially n or n plus 1, depending on whether we were odd or even. Yeah. So we were kind of, the constricting factor was that we had chosen equidistant quadrature points. And then we were stuck with this n or n plus 1 order of accuracy. We got around this by going to Gauss quadrature, or Gauss rules, Gauss quadrature rules. There we asked the question how to choose the quadrature points optimally. So in this case, this was asking how to pick the CIs now optimally to get the best order of accuracy, and there we found that doing that we managed to get order of accuracy 2n plus 1. So by moving the CIs around in quadrature, we ended up getting 2n plus 1 order of accuracy. And we know already that the order of accuracy of the quadrature rule is related to the consistency order of the Runge-Kutta method. In fact, we saw that if we have order of accuracy up to order p minus 1, then we get consistency order p. And so that means that we could potentially hope, so the hope would be that we can construct Runge-Kutta methods of consistency order two times s. So we hope that we can actually get consistency order that's twice the stage values, because we had if the first condition is satisfied for all monomials up to order p minus 1, then we can get consistency order p. We have s stages, so we have s points, so we can only get 2s is the maximum we can hope for. Okay. So before we do that, in the subsection 3.4.1, let's review some properties about Gauss quadrature that we have already done, and then I'm gonna tell you something about also two new methods, that quadrature methods that you have not seen probably, or at least the ones that did my numeric 0 have not seen, and that are called Radau and Lobato quadrature rules. So in this subsection, we review some of the basic facts of quadrature formulae based on orthogonal polynomials, such as Gauss quadrature. As I said, see numeric 0 for more details. Okay, so let Ln of t be the shifted Legendre polynomial of degree n on 0, 1. Okay, so in numeric 0, we always worked on the interval minus 1, 1. But for these quadrature rules, now we need to, for these Runge-Kutta methods, now we need to really go on to the interval 0, 1. So we shift, and we do this by subtracting a 1 here. And then you end up getting the shifted Legendre polynomials, and they can be compactly defined by this formula, which we've seen, or at least we've seen on the interval minus 1, 1 in numeric 0. So a quadrature formula for the integral 0, 1 f dx that uses the n roots of these Legendre polynomials as its quadrature points, and the integrals of the Lagrange interpolating polynomials at those points as its weights is called a Gauss rule. And then the first result that we're going to use is that the Gauss quadrature formula, so now I'm trying to use more the notation from numeric 0, the Gauss quadrature formula with n minus 1, with order n minus 1, so that uses n points. So in numeric 0, I actually worked usually with the n being the order, and then we have the number of points being n plus 1. So if we want the n point Gauss quadrature rules, then we have an n minus 1 here on the interval AB for approximating the general integral AB f dx is exact for all polynomials up to degree 2n minus 1 if, and this is now important, this is also the crucial condition for getting the high order Runge-Kutta methods afterwards, if we have sufficiently smooth integrand. So f has to be C2n. So then if the h is equal to b minus a, we have proved there in numeric 0 that then the quadrature rule has an error of order h to the 2n plus 1. And as I said, this can be seen in numeric 0 or the equivalent notes from wherever you did your first numerics course. And I said already the numbering is a little bit different in numeric 0, so I'm just gonna make that clear. Please note that in numeric 0 we numbered the quadrature nodes starting with 0. X naught up to xn minus 1 for the for qn minus 1, and thus here n, and thus n here is n minus 1 in the notes to numeric 0, which is a little bit confusing. I'm really sorry, but to define Runge-Kutta methods, we do always write the Butcher tableau starting with 1 and not with 0. And then I'll finish for today's video with the following second set of so there are an alternative set of quadrature formula called the Radau quadrature formula. They're the same, similar to Gauss rules, but they have they also use one of the endpoints of the interval 0, 1 plus the roots of the orthogonal polynomials. So as we will see, or it helps with stability later on to include one of the endpoints of the interval. Remember the 1-point Gauss rule just used the midpoint. The 2-point Gauss rule used the points on the interval minus 1, 1. It used the points minus square root of 3/3 plus square root of 3/3. And the Radau rules simply add one of the endpoints, the left or the right endpoint as well, plus the roots of the orthogonal polynomial with one order less. And then we distinguish either left and right Radau quadrature formulas depending on which endpoint we include. And then the Lobato quadrature, so Radau, and then the Lobato quadrature uses both endpoints and then uses polynomial of degree n minus 2 and the Legendre polynomial of degree n minus 2. Okay, so this here just they're all the Legendre polynomials. Just once with order n, with order n minus 1, and with order n minus 2. But for the Radau left, you need to do this shift, and with the Radau right, you need to do that shift. A Radau quadrature formula with n points is exact for polynomials of degree 2n minus 2. So you lose 1 over the Gauss, and the Lobato loses 2. So the Lobato is exact for polynomials of the degree 2n minus 3. Okay, so that's it for this section. In the next section, we will now define Runge-Kutta methods based on these quadrature formulae, and these Runge-Kutta methods are the so-called collocation methods. And that's what I'm going to do in the second video for this week later on. So that's it for today. Thanks.